Okay, so example 3. So 21.3. Now we're going to finally put things all together here. We're going to sketch solutions to graphs of inequalities. Okay, so let's start with something we know that we feel comfortable with. This is just a line here. This is a linear equation. So here is a graph that represents the solutions to the equation x minus y equals 5. And if we really wanted to, right, we could kind of get it into y equals, so x equals 5 plus y minus 5. So y equals x minus 5. So we know we start down here at negative 5, and we grow by a slope of 1. So we go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And sure enough, this represents our line here. Okay, now what we think about is, remember what we said, solutions to a line fall on the graph. For example, here's the point, 0 comma negative 5, x minus y. So 0 minus negative 5, does that equal 5? 5 equals 5. Sure enough, so this point is a solution on the line. What about this point here? This is at the point 5 comma 0. X minus y equals 5. 5 equals 5. So sure enough, this point is on the line. So what we're going to see, people, and what we said in the last example, is that all the solutions are all the points on this line. All the points on this line. Now, what's a little different is that inequalities, you got to choose your side of the line. So your solutions are either here on this side of the line, or they're down here on the other side of the line. That's the thing about inequalities. Now, with a line, solutions are on that line. With inequalities, they either have to be greater than the line or less than the line. So they're either above it or below it, or to the left or to the right. So the line splits the solutions and the non-solutions. And what we do is, the other thing that we do is, when we have solutions, we shade. That's how we represent all the solutions there are to an inequality. So we do some shading. Okay, so let's use that idea. Let's build on the idea of a line, and then we'll think about what this inequality is going to tell us. Okay, so think about if this were a linear equation. X minus y equals 5. Well, we know that it would cross here, and it would cross here. And watch this, I'm going to use a ruler. Look at this cool stuff going on here. And we know that the line would be like so. Okay, now this splits our graph. You see what I mean? This is section 1 and this is section 2. So let's think about, now we're really thinking about this inequality. So we need x minus y to be less than 5. Okay, so let's just go pick some easy points here. And you know what the easiest point ever to pick? You know what it is? You know what it is. 0, 0, right here. Okay, so if x is 0 minus y is 0, is that less than 5? Is 0 less than 5? The answer is yes. So this gets a solution. This gets a solution. And guess what, guys? Solutions can only exist either in area 1 or in area 2. I'm going to show you that area 2 doesn't exist. But as long as now we know that 0, 0 is a solution, all of this is our solution area. It's all being shaded. Look what I did here. I messed that up. It's all being shaded. But watch. We're gonna prove that area 2 doesn't exist. Okay, look. Let's pick a point like this. Negative 10. Whoa, where'd it go? Here we go. Negative 10. So 0 comma negative 10. So we're gonna test it. X is 0 minus y is less than 5. Minus a negative gives us 10. Is 10 less than 5? No way. So this is not a solution. Therefore, none of area 2 is a solution. So it's got to be area 1. So once you find a solution on either side of the line, every single thing on that side of the line also is your solution area. Now, the one thing that we got to go back to is we actually also need to test on the line, directly on the line. So here we go. Let's test this point right here. Let's test this point on the line, 5, 0. So x is 5, 0 is y. 5 minus 0, is that less than 5? Is 5 less than 5? No, it's actually not. So this point on the line gets the x, which means guess what? Every other point on the line is going to get the x. Every point on the line is going to get the x. So here's what we do. Instead of putting a bunch of little x's all along the line, because that's not going to look great. Here's what we do, people. What we do is this. We say, okay, guess what? I know where the line should be, but since the solutions aren't really on the line, we're going to make a dashed line to represent a boundary, but not part of the solutions. Only area 1, only this shaded region, area 1, is part of the solutions. Not the line, and certainly not the stuff down in area 2 below. Okay, let's do the same thing. Let's jump over to x minus y is less than or equal to 5. Okay, so again, think about the line x minus y equals 5. We know it has a point here and it has a point here. We're going to use our cool ruler. We're going to connect these 2 points. Now, once again, think about area 1, area 2. Test the point 0, 0. It's super duper easy. 0 minus 0, is that less than or equal to 5? 0 is less than or equal to 5. You betcha. This is a solution. Therefore, area 1 gets the solution, gets the shading. Boo, area 2. Area 2's got nothing done there. Now, guys, what's the only difference here? Look at this symbol. Less than or equal to, less than. Well, guess what? What did we say when it's equal to? It means solutions are on the line. Well, if it's less than or equal to, it means we must have solutions on the line. So in this case, since the line counts, we keep it a solid line because the line counts. Over here, we made it dashed because it was strictly less than. So we just needed to represent a boundary. In this case, it's a solid line. So we put our shading, look, we put our shading right up against that line because the line is included. Okay, let's keep it rolling. Hopefully we should pick up on a pattern here so that we don't have to do as much together. Okay, here we go. X minus y is greater than 5. So think about the line x minus y equals 5. It exists. We know where that line exists. And I'm just using that from the example above. Now here's my question. Like, should I just kind of save my time here and not really, like, should I really just draw on a solid line? No. Why am I not going to draw on a solid line? Because, people, this is strictly greater than. If it doesn't include the line, we can't make it solid. So right away, we should be thinking, hey, let's just make it dashed because we know that it doesn't include equal to the line. So we might as well make it dashed. And now we have area 1 and area 2. I think, again, look at how the only difference, guys, is that the inequality symbol flipped. Look at this and look at this. So I think we should have an idea of where the solutions are going to be, but let's just test a point real quick. Easiest point to test, that is 0, 0. 0 minus 0, is it greater than 5? Is 0 greater than 5? No way. So 0, 0 is out, which means area 1 is out, which means where do our solutions exist? You guessed it, all in area 2. And it's a dashed line because it is what we call a strict inequality. It is just greater than. So let's put this all together here. Let's see if we can just do this right away. So x minus 5 is greater than or equal to 5. So we know that the line Should we have dashed or solid? Think about dashed or solid. Yes, we're going to have solid because this includes the equal to, and we know that solutions of a line are on the line. So we keep it solid, and then we say, okay, x minus y needs to be greater than 5. So pick your point 0, 0. 0 minus 0 is 0. Is 0 greater than or equal to 5? Absolutely not, which means this area is out of the running, which means it must be, all of our solutions must exist down here below the line. And we keep it solid. Okay, so look at what we did here. So we're thinking about area 1 versus area 2, testing that really easy point 0, 0, and then thinking, does that make my inequality true? If so, shade that side of the line. If it doesn't, you know it's got to be the other side of the line. Keep it dashed if it's strictly less than or greater than. Include the solid line if you have that equal to bar underneath.